We're going to take a look at a proof of the midsegment theorem. So what the midsegment theorem says is that if a segment connects the midpoints of two sides of a triangle, then it's both parallel to and half the length of the third side. So to do this, what we're actually going to use is a different type of proof. It's called coordinate proof. And what it allows us to do is kind of take a more analytic look at something. And so since we're talking about parallel, which is something that's easy to talk about, in the Cartesian coordinate system using slope, or half the length of, which is obviously using measurement, it makes sense to take a little bit more analytic look at this. So the way that we're going to go about this is we're going to take a look at a coordinate plane and kind of place a triangle in there that we can then manipulate to prove what we want it to. So what we're going to do is start by drawing that coordinate plane. So I guess I don't need all of this. I'm just going to have the top half. Alright, so if I have my coordinate plane, this is my x-axis, and this is my y-axis. And what I'm going to do is I'm going to place a triangle in there that could represent any triangle. So there's nothing specific to it. It's not isosceles, it's not right, it's not anything. It could be any triangle. So the way that we're going to do that is we're going to pick some points that are representative of that. So what I'm going to do is I'm going to pick the point 0, 0 is just always a good starting point. It's a good number to use. I kind of need a grounding somewhere. So 0, 0. And then I'm going to pick a point that, one of the sides I'm going to have along my x-axis here, which will make sense. And because the side can be anywhere, it doesn't really matter. This isn't, locking me into anything. And what I'm actually going to do here is do something that's a little bit weird. I'm going to give this a value of, let's go with 2c, 0. And it'll become clear why I want to do that in a little bit. But I'm just giving this variable c. It's over here someplace, no big deal. This segment could be part of any triangle. And so the last thing I need to do is pick another point out here. I'm going to pick this one here to make my triangle. And so when I pick the coordinates now, what I want to do is pick them so that, again, it doesn't lock me into anything. So I'm not going to give it number values. I'm not going to give it anything to do with c. I'm just going to pick two other variables, a and b. But I'm going to do the same thing again, which is call it 2a, 2b. And so the whole point of me doing this is that, if I want to show that this extends to right triangles, for example, I could make a 0. And so that would take this point over here, put it on the y-axis, and I'd be talking about a right triangle then. If I wanted this to be specifically isosceles, then I could make the value of a to be, half of c. So it's right in the middle of these two endpoints here. And so it'd be an isosceles triangle. So point being is that I could pick values of a and b or c for that matter to make any triangle that I wanted to. I'm not locked in anything specific here. Okay, so now I need the midsegment, which connects to the midpoints. What I'm going to do is pick this one right here. So I'm just going to draw on my midpoints. And the reason that I picked the values I did previously was so now I can talk about these. So how do I find the midpoints? Just the average of my x-coordinates and my average of my y-coordinates. And so the average of 2a and 0 is just a. And the average of 2b and 0 is b. So it comes out to be nice numbers. So that's the only reason I picked 2a and 2b, just so that it worked out nicely there. And I can do the same thing here. What's the average of 2a plus 2c? So 2a plus 2c divided by 2 is just a plus c. And the average of 2b and 0 is, of course, just b again. Okay. So now I've got two things I need to prove. I need to prove that... Let's see. So let's actually write this out. I'm trying to prove that I should name these points. How about that? A, B, C, D, and E. I'm trying to prove that DE is parallel to AC and that DE is half the length of AC. Okay, these are two things I'm trying to prove. So I'm going to work through those now. Let us start with the parallel part. So how do I show that two things are parallel? I can show two things are parallel just by talking about their slopes. If they have the same slope, then I'm good. So let's go ahead and find that. Let's use a different color. Let's say that I want to find the slope of, let's start with the slope of AC. So I'm going to use M to denote my slope, and I know that I'm talking about AC, I'm going to call it the subscript AC. The slope of it will be, okay, so my change in Y, which is 0 minus 0, over my change in X, which is 2C minus 0. And so what that simplifies is to just 0 over 2C, which is 0. And that makes sense because we picked this to be a horizontal line. Of course, it could have been any, but so the slope comes out to be 0. So the interesting thing is that even though we picked AC to be what it was, DE still has to have the same slope, and so we'll find that out, see if it does here in a second, by finding the slope of DE, which will be, all right, so change in Y, B minus B, over change in X, A plus C minus A plus C minus A, which simplifies to 0 over C, and that's also 0. So what we found here is that they have the same slope. So even though I did pick A and AC to have a slope of 0, DE has to have the same slope, no matter what. So what I can say is, thus, the slope of AC is equal to the slope of DE, and therefore AC is parallel to DE. All right, so that's step 1. I am now done proving the parallel part. So now I'm going to prove my length portion. Let's see, what color do I want to pick? Let's go with this. That might be too dark. We'll find out. Okay, so let's find lengths here. So as we just talked about, the thing that works out nicely here is that they're both horizontal lines. And so when I go to find distance here, I actually don't have to use my distance formula. Generally speaking, I would. But since these are horizontal lines, I can just count over in my x direction. So the length of AC will be equal to, well, 2C minus 0, which is just equal to 2C. Okay, so that's the length of AC. The length of DE then, is equal to, all right, since my y values are the same, I'm just going to have A plus C, the ending point, minus my starting point, which is A, so I'll be equal to C. All right, perfect. So what that means is, thus, AC is equal to 2C, I should put that lowercase, 2C, which is equal to, just a way I could rewrite that is 1/2 of, well, actually that's not how I want to do it. I want to write this as is equal to 2C. Undo. What is 2C equal to? What is C equal to? Well, C is just equal, yeah, I was making this way harder. I want it to be 2 times DE, which is exactly what I wanted to show. Therefore, AC is equal to 2 times DE. Oh, I guess that wasn't actually what I wanted to show. I want to show that DE was equal to, oh man, I made mistakes all over the place. AC is equal to 2 times DE. Do I have an eraser? Never actually had to use my eraser before. I'm just going to cross this out. DE. There we go. Yeah, I'll divide by 2. I'm making this a lot harder than what it needs to be. That's okay, though. There we go. So, there we go. Those are 2 things I need to prove. Again, I chose to use this coordinate proof here because the things I was trying to prove were a little bit more analytic. They had some computation involved, and so I set up this triangle that could represent any triangle here in my coordinate plane, but I used variables so that it could represent any triangle, and then just use my computation here to find the slopes and show that they're parallel, and to find the lengths and show that one's half the other. So that's why coordinate proof can be really helpful to me, is that if I want to do calculation-based things, I can do that. So that's the proof of the mid-segment theorem. It just says that if I have a mid-segment of a triangle, then it will be both parallel to and half the length of the opposite side.